right, so let's start 3.4, the derivative as rate of change. So as we discussed in section 3.1 and 3.2, uh, when we talk about the concept of the derivative, one of the interpretations for the derivative is the instantaneous rate of change of a given function with respect to a specific point x of 0, okay, and which is defined as a limited definition. So in this section, we're going to talk about a couple of examples, but first of all, let's look at this example here, and it described into this way. So everybody knows that the area of a circle is related to its radius by this equation. Area equals pi I squared, right? R stands for the radius. And here we have a question like this. How fast does the area change with respect to the radius when the radius equals 5 meters? Of course, it's a very large circle, okay? What does that mean? That means like this, okay? So, when the radius keeps changing, okay? And you see that the area is also keep changing, right? So when the radius is becoming larger, the area for sure is becoming larger. But what is like the changing rate um, with respect to the radius when the radius equals 5? In other words, how fast, okay, the area is changing at the moment when the radius equals 5. Actually, this problem we can use the derivative as rate of change to handle it, well, instantaneous rate of change. So we know that right now area is a function with respect to the radius, right? So it's a pi r squared. And then if we take the derivative, okay, of this, which gonna based on the power rule, we're gonna have it's 2 pi r, right? 2 pi r. And you see that this is gonna be the area rate of change with respect to the radius. And we know that when the radius equals 5, so we're gonna have 2 pi times 5, which gives us is 10 pi, okay? And of course, the unit is gonna meter square over meter, okay? So that's how do we do this problem here. And okay, so this is just the first part, a very short pieces for the derivative as the instantaneous rate of change. So on the second part, I'm going to talk about, if you have a moving object, and, of course, you're going to have like a distance function of that moving object, and also corresponding to the velocity function, the acceleration function, what is the relationship of that, okay? So I'll be back soon.